Welcome to the second or third physics lesson, depending on your perspective. This one will be about free body diagrams, featuring me, Aaron, and Eva, and also Sir Isaac Newton in the background of our title slide. So, yeah. Okay, there we go. So you're probably wondering, what are free body diagrams? They are diagrams, which is a fun fact, actually. And essentially, they are illustrations that show how forces interact with each other and how they act on an object. They can be drawn for pretty much anything in existence, and they're a way to increase our understanding of how forces work throughout the universe.
Okay, so very well said. And this right here on the screen is an example of a free body diagram. You can think of this as a book resting on a surface, okay? So how this kind of leads us to the question of, well, how do they work? So arrows are used to represent forces. In this example, there's normal force going up and gravitational force going down. And the direction of the arrow that the arrow is pointed is the direction of the force. And the longer the arrow, the stronger the force, and the shorter the arrow, the weaker the force. Now in this case, the arrows are the same length, which just means that the object is not accelerating. Okay, so let's try and make our own free body diagram. And we're going to use this picture as an example. It's a person trying to move a fridge, but because the arrows are the same length, there isn't going to be any acceleration. So all of our arrows are going to be the same length. Now, we start with just drawing kind of like a circle in the middle of our drawing, and this represents the mass, in this case, the refrigerator. And now we have, we're drawing, now it's time to draw the arrows. So we have the applied force that is seen here. And this applied force is going to be going in the same direction that it's applied, just like that. And then we have friction force pushing against this. It's also going to be the same length. So I'm just going to try to make it the same length. But yeah, okay, that seems pretty even. And then just because these are the only ones that we actually see at work here does not mean that there aren't any other forces, so there's always going to be force of gravity, which in this case is going to be going down, and then normal force pushing up against the fridge, that's kind of opposing gravity, just like that. So if we wanted to add some captions here, this would just be normal force. Over here would be applied force, and it's going to be applied by the person, so we can just note that here. Then we have gravitational force, I can spell, and then we have, one moment here, okay, and then we have friction force acting against this. So this is just an example of a free body diagram from this drawing. Okay. Let me just clear this drawing. Okay, there we go.
Okay, well said, Eva. All right, so let's try some more examples. This one is of a box moving across the surface. We did represent this with questions, but I guess we forgot to do the animation, so here it is. So essentially, the normal force and the gravitational force, F of G and F of N, cancel each other out, as you can see with the red and blue arrows. Thank you for the arrows there, Eva. Mm-hmm. Then we have the friction force and then the applied force on this box moving across the surface. And as you can see, the applied force is greater than the friction force, which means that this box is accelerating to the right, or in the direction of the applied force. So this is how you would draw an object that is accelerating towards the right. Okay, so let's go to a very complicated example. It's quite a leap. But for this one, we have two blocks and what looks like a rope or a wire holding on to this block A, and then block B is below block A. And essentially, you have the normal force from B pushing up on block A, and then you have the friction force as B is sliding down this slope and A is being pulled back. And it appears these are at rest, um, and as such, the friction force is canceled out by the tension force. Well, actually, in this diagram, the blocks are being pulled back upwards because the tension is greater than the friction force exerted by B on A. Then you have the weight of block A, which is actually just the force of gravity broken down into different parts. So you have one force of gravity actually going directly down on block B, counteracting the normal force by block B. And then you have another part that is going in the direction of the friction force, essentially making these two blocks at rest, because part of this gravitational force will actually go down the direction of the slope, which cancels out the tension along with the friction.
Okay, and there's actually one more thing that I should probably mention, and that's the way in which we represent that forces are equal in these free body diagrams, which I'm so sorry I should have mentioned earlier, but let's just use these two as an example. And we have our little fridge in the middle here. If we were to want to represent that the applied force is the same as the friction force going back, we just need to draw a little two little dashed lines like so, and that shows that these two are equal here. So yeah, thank you for listening to our forces presentation, free body diagram presentation.